IEEE 802.1 AD is an Ethernet networking standard informally known as QINQ and is an amendment to IEEE standard IEEE 802.1 Q 1998. The technique is also known as provider bridging, stacked VLANs, or simply QINQ or Q&Q. Q&Q can for supported devices apply to C-tag stacking on C-tag, but this has limited application in the modern methodology of network routing. The original 802.1Q specification allows a single virtual local area network header to be inserted into an Ethernet frame. QINQ allows multiple VLAN tags to be inserted into a single frame, an essential capability for implementing Metro Ethernet network topologies. Just as QINQ extends 802.1Q, QINQ itself is extended by other Metro Ethernet protocols. In a multiple VLAN header context, out of convenience the term VLAN tag, or just tag for short, is often used in place of 802.1Q VLAN header. QINQ allows multiple VLAN tags in an Ethernet frame. Together these tags constitute a tag stack. When used in the context of an Ethernet frame, a QINQ frame is a frame that has two VLAN 802.1Q headers. Background: 802.1 AD specifies architecture and bridge protocols to provide separate instances of the MAC services to multiple independent users of a bridged local area network in a manner that does not require cooperation among the users, and requires a minimum amount of cooperation between the users and the provider of the MAC service. The idea is to provide, for example, the possibility for customers to run their own VLANs inside service providers' provided VLAN. This way the service provider can just configure one VLAN for the customer and customer can then treat that VLAN as if it was a trunk. IEEE 802.1 AD was created for the following reasons. 802.1Q has a 12-bit VLAN ID field, which is a theoretical limit of 212 equals 4096 tags. With the growth of networks, this limitation has become more acute. A double-tagged frame has a theoretical limitation of 4096A. 4096 equals 16,777,216, sufficient to accommodate network growth for the next several years. The addition of a second tag allows operations that would not have been available had the VLAN ID field simply been expanded from 12 bits to 24 bits. Having multiple tags the tag stack allows switches to more easily modify frames. In a tag stack scheme, switches can add, remove or modify single or multiple tags. A multi-tagged frame not only has multiple VLAN IDs, but has multiple VLAN header bit fields. A tag stack creates a mechanism for Internet service providers to encapsulate customer single-tagged 802.1Q traffic with a single tag, the final frame being a QINQ frame. The outer tag is used to identify and segregate traffic from different customers. The inner tag is preserved from the original frame. QINQ frames are convenient means of constructing Layer 2 tunnels, or applying quality of service policies, etc. 802.1 AD is upward compatible with 802.1Q. Although 802.1 AD is limited to 2 tags, there is no ceiling on the standard limiting a single frame to more than 2 tags, allowing for growth in the protocol. In practice, service provider topologies often anticipate and utilize frames having more than 2 tags. It is easier for networking equipment makers to modify their existing equipment by creating multiple 802.1Q headers than to modify their equipment to implement some hypothetical new non-802.1Q extended VLAN ID field header. Frame format. These examples are for an Ethernet 2 framing frame. This could also be applied to 802.3 frames, with or without an LLC plus snap header. The top frame is a simple Ethernet 2 frame. The middle frame has a 0.1Q tag added to it. The bottom frame has yet another 0.1Q tag added to it. A 0.1Q header, which is 4 bytes long, is added to an untagged Ethernet 2 frame in the following manner. The 4-byte tag is inserted between the MAC source address of the untagged frame and its ether type field. The newly inserted VLAN header's ether type is set to 0x8100 to identify the following data as a VLAN tag. 12 bits are used for the VLAN ID, the other bits in the VLAN fields are filled in according to the COS policy, etc. of the interface at which the tag imposition occurred. Notice that after the insertion of a 0.1Q header to an untagged frame, the frame's original ether type appears to have been changed to 0x8100. The untagged frame's original ether type in the single tag frame is now located adjacent to the payload. Its value is unchanged. A second 0.1Q header is added to a single tagged frame in the following manner: the second tag is inserted in front of the first tag, meaning the second tag is closer to the Ethernet header than the first tag. The second tag is inserted between the MAC SAMAC and the first tag. The second tag is assigned an ether type of 0x88A8 by default. 12 bits are used for the VLAN ID, the other bits in the VLAN fields are filled in according to the COS policy, etc. of the interface at which the tag imposition occurred. Any third or subsequent tag imposition will insert the tag in front of, closest to the Ethernet header, than the preceding tags. The frame's original ether type is always located above all the tags, next to the payload. In the case of an 802.3 frame, this ether type would be a length value instead, and would contain the length from there to the end of the frame. In the case of an 802.3 frame with an LLC header, the LLC header stays above the length field, adjacent to the payload. The conventions for 802.1 AD terminology typically are as follows: the inner tag is the tag which is closest to the payload portion of the frame. It is officially called C tag. The outer tag is the one closest to the Ethernet header. Its name is S tag. Tag 1 is the outer tag. Tag 2, the second tag, is the inner tag. The tag number has nothing to do with the order in which the tags were added, etc. It is simply a convention. For a single tagged frame, the tag is designated tag 1 when mixed with 802.1 AD tags. In frames having more than one tag, the tags are numbered 1 to n, and appear sequentially and contiguously in the frame from Ethernet header to payload. In this case the innermost tag is the CTAG and all other tags are STAGs. In IEEE 802.1 AD the CFI is replaced by a drop eligibility indicator, increasing the functionality of the PCP field. Tag operations: in a tag stack, push and pop operations are done at the outer tag end of the stack, therefore, the tag added by a tag push operation becomes a new outer tag. The tag to be removed by a tag pop operation is the current outer tag. Examples: virtual networks equals. This simple example will illustrate a practical use of 802.1 AD. The diagram shows switches as hexagons, and a service provider network encompassing all items within the dotted oval. The items on the periphery of the oval are networks belonging to SP customers. Different physical locations appear in the shaded rectangle, and include both customer and SP network components. A service provider offers L2 connectivity to customers in the cities of Seattle and Tacoma. Two corporations, Acme and XYZ, have a campus located in both Seattle and Tacoma. All campuses run Ethernet LANs, and the customers intend to connect through the SP's L2 VPN network so that their campuses are in the same LAN. It is desirable for Acme and XYZ to have a single LAN in both Seattle and Tacoma, obviating the alternative of having two LANs in which traffic must be routed between the LANs. The SP has two switches, one in Seattle, and one in Tacoma. The customers interface to the SP network in switches designated A and B. Each customer has its own pair of A and B switches. Acme's switch A is connected to S switch number 1 through link A1. The rest of the links are labeled. S switch number 1 and number 2 are connected by link S12. Acme's LAN uses VLAN IDs 10, 11, 12 in their network. The connections A1 and A2 are Ethernet trunks that have single-tagged VLAN traffic, the traffic using IDs 10, 11, 12. Likewise XYZ uses IDs 11, 12, 13 in their network, so X1 and X2 are also trunks with single tag traffic of IDs 11, 12, 13. The SP, having one network and one connection between S-switch number 1 and S-switch number 2, must segregate ACME's and XYZ's traffic. Since both ACME and XYZ share some VLAN IDs, traffic cannot be segregated by customer VLAN ID. The solution is for the SP to use 802.1 add in their network. They assign a single, unique outer VLAN tag ID of 100 for ACME, and a unique outer VLAN ID of 101 for XYZ. All traffic sent from ACME A to the SP network will have a tag of ID equals 100 pushed. The inner tag will be either 10, 11, 12, the original ACME tag. The traffic will be sent through S12 in this format, and just before it exits S-switch number 2 bound for ACME B, all traffic will undergo a single pop operation, removing the outer VLAN tag with the ID 100. This pop operation is the inverse of the former push operation, with the net result of no change to the traffic. The traffic passes through the SP network as 802.1 add frames, but no 802.1 add frames are sent to or received from the customer. Problems with previous example. An experienced network engineer will immediately recognize the shortcomings of the above example. This is the reason why 802.1 add is more of a definition for a method of adding multiple tags to a frame than it is an end-to-end self-contained solution. It is used in conjunction with other protocols and standards. The problems with the above example are: many switches bridge Ethernet traffic based on MAC addresses not on VLAN IDs. This is called shared VLAN learning and is done per 802.1d MAC learning, MAC aging, etc. Should ACME and XYZ use the same MAC addresses in their networks, this will cause problems with the MAC learning, as the assumption in MAC learning is that no two hosts use the same MAC address. In other words, a MAC should only be learned from a single switch's port. The SP network must learn all customer MAC addresses in order to switch them. This does not scale well. There is no provision in the above example for L2 protocol frames, spanning tree being the most important. Additional CoS capabilities are lacking. Bridges that use independent VLAN learning, that is, the first VLAN tag is included as part of the SAMAC address, circumvent the problems mentioned in paragraphs 1 and 2. IVL resolves the problem of MAC addresses possibly being used by more than one customer. However, switches en route still have to learn all inserted VLAN MAC address combinations. Broadcasts from LAN to LAN is always an issue to consider. Provider bridges and provider backbone bridges address the above problems by a further modified SAMAC learning method. See also, Connection-Oriented Ethernet, Carrier Ethernet, Metro Ethernet, IEEE 802.1, IEEE 802.1 or 2008 Provider Backbone Bridges, IEEE 802.1 AC Shortest Path Bridging, Provider Backbone Bridge Traffic Engineering. References. External links, IEEE 802.1 Add Official Page, IEEE 802.1 Q&Q VLAN Tag Termination, Stacked VLAN Processing, Configuring Super Aggregated VLANs.